Welcome to another episode of Measurement and Measurable series. In part 2, we are discussing errors, that is, experimental errors. However, to keep our videos short, we split this one into two halves. This is the first half where we discuss the basic things about experimental errors. An experimental result is never exact. Suppose you are measuring with a digital weighing scale so as to avoid any error on your part, you just have to take down the number. The scale you are using happens to be absolutely error free. Then, of course, there is no such scale as absolutely error free, but hypothetically, let us assume you have one. However, it has a 5-digit display. For some object, the display reads 01.203 units. Now think, how would you convince yourself that the actual weight of the object is not 01.2031 or 01.2033? Maybe you can get a finer scale. This time the uncertainty will be a bit smaller. Nevertheless, there will be uncertainty. If you go on increasing the efficiency of your device, you are going to face another problem. At some point, your device will be so sensitive that every dust particle present on the device or on the object will contribute to some variation. In that way, you will be plagued with another sort of uncertainty. Moreover, do you know for sure that an error-free apparatus remains error-free over the course of time? Maybe its internal circuit or sensor degrades. Now, if you are measuring because you need this value for some other experiment, then you are carrying this uncertainty forward. As it happens, that there are more reasons to worry about the errors apart from the limitation of the apparatus. Over the years, scientists have made a detailed study of the errors. We cannot eliminate all the uncertainties, but we can control them. More importantly, you can make a clear estimation of uncertainties present in the final result. Now, this is the hierarchical tree of error. This is how errors are classified. Now, let us briefly talk about each one of them. Gross error. Gross errors occurs mainly due to the experimentalist's fault. For example, writing a wrong reading. And the only way to avoid gross errors is to become very careful. Random errors fluctuate from one measurement to another. They may be due to poor instrument sensitivity, random noise, random external disturbances, and statistical fluctuation. The point is, we do not know for sure what causes random error, and thus we do not have any control over that. However, we can minimize random error by taking numerous measurements and then taking an average. We'll discuss it later. Observational error results from faulty study of reading, may be due to parallax. Now, you have heard about parallax when your teacher said that when measuring some object with even a simple scale, your eye should be at the level of the scale markings so as to avoid parallax error. Some of the better equipments do invent ways to avoid reading that are plagued with parallax errors or that are prone to parallax error rather. However, if you do not have them, you just have to learn about parallax errors and how to avoid them. Environmental error happens due to outside situation of the measuring instrument, such as temperature change, force, moisture, dart, vibration, otherwise because of electric field and magnetic field in the vicinity. They also take a toll on your apparatus. Your apparatus might get rust and sensitivity changes, etc. So to avoid this kind of error, you have to maintain your equipment and try to perform your experiment in a stable environment. For example, not in the close proximity of a very strong electric or magnetic field, and doing the experiment during that part of the day where the temperature fluctuates less. Well, temperature will always fluctuate throughout the day, but perhaps you can steal a window of say 1 hour within which you will perform the experiment and within which the temperature doesn't change much. Then your environment is stable as long as temperature variation is concerned. Inherent limitation is an instrumental error, typically inherent problem of the apparatus, and perhaps the only possible way to eliminate this sort of error is to use a different apparatus. Abuse of apparatus. Now, an otherwise good apparatus can behave erratically in the hand of a novice experimentalist. For example, the abuse of an apparatus may cause the breakdown which changes the zero of the tools. Then all the subsequent readings will be plagued with some sort of systematic error. Either they will be enhanced or they will be decreased. So learn to use your equipment properly. Finally, the effect of loading is caused by the instrument in measurement work. For example, when the voltmeter is connected to the high resistance circuit, it gives a misleading reading. On the other hand, when it is connected to the low resistance circuit, it gives the dependable reading. This means that the voltmeter has a loading effect on the circuit. So learn to use your equipment properly and also learn about the limitation of certain equipments. That will help you avoid this kind of systematic error. Now, this is a good place to talk about accuracy and precision. They may appear synonymous, and in fact, in our everyday life, We do use these words interchangeably, but their meaning is vastly different in scientific context. Accuracy refers to the correctness and means how close the result is to the true value. Precision, on the other hand, means the degree of exactness of the experiment or how well the result has been obtained. Precision never refers to true value, it is just a quality attribute. In terms of error, accuracy depends on how well the systematic errors are compensated, whereas precision depends on how well the random errors are managed. In an experiment, we should always consider both, as all the measurements are subject to both sort of uncertainties. Now, this figure demonstrates the difference between accuracy and precision. Notice in the first figure, only one hole is punched through the bullseye, and holes are scattered. This is a low accuracy, low precision experiment. In the second figure, the holes are clustered but farther away from the bullseye. So, although it is of high precision experiment, it is low in accuracy. The accuracy improves in the third figure, but at the cost of precision. See, the holes are scattered, although 3 of them hits the bullseye. Finally, we have a cluster of holes within the bullseye, which is high accuracy and high precision. So, if you forget about gross error, that is, you be extremely careful, then you have to deal with systematic error and random error. Although there are subclasses of systematic error, all of them have common features. For example, systematic error is predictable and typically constant or proportional to the true value. If the cause of the systematic error can be identified, then it usually can be eliminated. Another property of the systematic error is it is often one-sided. That is, either it enhances the final result or decreases it. Random error, on the other hand, is always present in a measurement. We do not have any possible way of eliminating random error. However, we can control them, and more importantly, as I mentioned, we can estimate random error in the final result. In what follows, we shall deal with random errors only. However, some of the definitions are valid for any kind of error. Suppose we are measuring certain quantity which has a true value of xt, but we get a measured value of x. Then we defined absolute error as xt minus x. Now, depending on whether x is greater than xt or less than xt, it is either negative or positive. However, absolute error is not much useful. For example, consider two situations. In the first place, you are measuring a 100-meter long object and come up with a measured value of 99.5. In the second place, you measure a 10 centimeter long object but has an experimental result of 9.95 centimeter. So if you calculate absolute error, in the first case you have an absolute error of 0.5 meter, whereas in the second case you have an absolute error of 0.05 centimeter. So in terms of absolute error, it seems that the second case is the more precise. However, remember, to get a correct picture, you have to sort of express this error as a fraction of the true value. That we do in relative error. Relative error is just absolute error divided by the true value. Now, if you compute relative error in both the cases, you will get exactly same result as 0.005. So it seems that both the cases are equally precise. Evidently, it is more prudent to talk about relative errors. We can also define percentage errors, which is a slight variation of relative error. It's just relative error times 100. It's just different way of expressing relative error. Now, these are the formulae to sum up. Notice that xt stands for true value of some quantity, x stands for the measured value of the quantity. Now, we don't have any problem with the measured value of the quantity. However, with the true value of quantity, here is the big question. But how do you know the true value? Well, the answer lies in the second part.